We're moving on to a new topic, our second topic, which has to do with, well, essentially it's Newton's laws, all right? We are all familiar with Newton's laws.
Yes.
Hey, do we have, let's remind ourselves of what we know about Newton and his crazy laws.
Crazy.
All right, what are Newton's laws?
If an object in motion is made in motion to blah blah blah. Inertia.
Ta-da! Inertia. Very good. All right, the deal is this. I want you to remember it this way, please. An object in motion stays in straight line, which is linear, constant velocity motion. Yes.
So that's like the angular stuff.
We'll talk about that. Because there is an angular equivalent, okay? And we'll talk about that. Actually, I'll talk about it in just a minute. Thanks for bringing that up. Okay, listen up, everybody. Come on. All right. Inertia, I want you to remember it this way. An object in motion stays in straight line, which is linear, constant velocity motion. Okay? Straight line, linear, constant velocity motion. Unless. What's the unless part? Unless it's acted on by a net force. Okay, now there are a couple things about this that are important. Okay, so we got constant velocity, straight line, linear motion. All right, here's the deal. Constant velocity, that can be of two varieties. You can have a constant velocity where the velocity is zero, which is at rest, or just any kind of constant. Okay? Constant velocity of zero is literally a constant of zero, right? We kind of think of that as different because it appears different to us, okay? But rest at zero velocity is one of the natural motions of objects. And straight line linear motion at a constant speed, not turning, is the other kind. So essentially what we're talking about here is acceleration equals zero, right? Acceleration equals zero. All right. And we have acceleration equals zero whenever the net force equals zero, right? When that equals zero, then the acceleration equals zero. So that means it won't change speed and it won't turn. Okay? That's it. So really the first law of Newton is really a subset of the second law of Newton, which is F equals ma essentially. First law is really this law when there's no net force, okay? So remember, there can be lots and lots of forces going on. It's just that they're all canceling out. So you can either have no forces at all, or you can have lots of forces. They just cancel out. No acceleration. So it's either at rest or it's going to move it at a constant speed, straight line, okay? So you're looking for a couple of key words when you run across these problems. You're looking for the key word of at rest, or you're looking for constant velocity, or straight line, linear, constant speed motion, okay? All right, if you have a net force, then you get this. It's going to accelerate. And this is a vector equation, so the net direction of the force will be the net direction of the acceleration. Okay? Now that's going to give us, remember, acceleration comes in two varieties, right? We have our centripetal acceleration and we have our tangential acceleration. So if the object, if that net force is along the path only, then it's only tangential. You're just going to speed up or slow down. If the net force is off axis, meaning that it's not pointing just in the direction it's going, then it's going to turn as well, right? Okay. And then we have the lovely third law. Actually, before we do that, Raul asked a question. He said, does this apply to rotational motion as well? This inertia thing. And the answer is yes, but it's a little different. okay? The rotational equivalent of Newton's first law is, well here, let me give you the rotational equivalent of F equals ma. The rotational equivalent is torque. The sum of the torques equals I alpha. Okay? Now y'all know what torque is already. Okay, torque, what is torque?
Rotation. It's force rotation.
It's a force, but it causes something to rotate because it's a force that acts through a radius, right? Okay? So you can have a force without having a torque,
But you can't have a torque without a force.
but you can't have a torque without a force. Is it possible to grab hold of the doorknob and push on the doorknob and not have the door rotate?
If the door is broken.
But if the door is free to rotate,
Yeah. It's free to rotate. Oh, he means you just grab it and you don't repeat that.
is it possible like to grab hold of a door? Like for instance, this door right
Pull it
here.
out, like you can cut it out here.
Is it possible for me to apply a force somewhere here at the handle and not make it rotate?
Yes. If you straight
If you
in.
pull on it.
Yeah, if I pull on it, or if I push on it, right? Pull or push, nothing happens. I'm gonna pull the whole thing over. All right, so remember there's an angle involved in there, right?
Yeah.
So we're a little ahead of where we want to be right now, but torque equals what?
I'm still confused on what the torque is.
Okay, here you go. Torque equals R cross F. Okay? Remember cross products from last year?
We never did cross products in the science class.
Okay, you remember cross products in my class?
We're doing it
No.
this year.
Because we didn't do it.
All right.
I don't know what we're talking about.
A dot B equals
Okay, we didn't do it in
A
our class.
cross B equals.
Wait a minute.
Dot product, cross product.
This is having a test.
In the cross product, you multiply like the two components of the vectors, like the 2x and 2y, or is it? No, it's crosses. I definitely don't know how to.
Dot product is the easier one.
Isn't it?
Algebraically, it's A, B, cosine theta of the angle in between the two. And this is a scalar.
When did this happen? Did you know about this? No.
Yes.
This is a scalar
I've
product.
been doing this all year.
Okay?
All year, it's been 3
Hey, wait,
weeks.
what are we going over exactly?
We don't have it.
What's that?
What are we going over?
Well, the question was, we got sidetracked. The sidetrack was that some people didn't remember what torque was.
No. I need to know what the title of my notes.
Forces, dynamics, Newton's laws. Okay, here we go, everybody. Just as a quick note, we'll go over these when we get to them. But there's two ways to multiply vectors, dot product and cross product. Dot product is a vector times a vector, which gives you a scalar. We use this with work. Okay? Remember F cross X, dot X is Fx cosine theta. Remember that?
No.
Oh.
Uh-oh.
We see that one.
Yes, like.
I think last year I was actually delta R maybe instead of
Okay,
X.
yeah.
Delta R?
I get it. Wait, I don't know. I've never done
Okay? Gives you a scalar. All right. We saw this last year when we did magnetic fields. This is A, B, sine theta. Okay? And this is a vector. All right. Do you remember this equation from last year? Magnetic force equals Q, B, B, sine theta. Okay? Okay, now do you remember this? Do you remember the direction of the force? Remember this craziness of you've got your B field doing this? And your proton moving that way. Which way's the force? Do you remember?
Up.
Right hand rule. Point your fingers in the direction it's going. Curl your fingers in the direction of the B field. And your thumb points up. So the force is this way. All right. Now, we won't run across this until springtime.
Thank God.
All right.
Wait, why did we get into?
But the deal is this. Yeah. It's the curl your finger deal. All right. Now, listen up. Hey, listen up. This is a cross product. Technically, it's QV cross B. Okay? That's technically what it is.
Oh.
All right. Torque is a cross product. And we'll talk more about this when we get to torque. But the deal is that torque is a vector. But the crazy thing about cross products is you get your vector in the third dimension, right? Okay. So if your radius is this way, your force is this way, radius is this way, say your force is this way, the torque will be up. So that's kind of weird, and we'll talk about that when we get there. Okay? So don't get freaked out by it yet. Okay, the deal is this though. Torque is a force and a radius, which is RF sine theta. And the reason why you can pull on the door, even though you've got a force and the radius, here's your hinge right here, here's the radius right here, here's your force right here. So you have a force and you have a radius, right? But there's no torque because the angle's not right. Okay? Sine of 180 or sine of 0 would still give you a torque of 0, right? Okay, so the deal is this. The angular equivalent of F equals ma is torque equals I alpha. So if there is a net torque, a force and a radius and the right sign, then what will it do? It will give you a angular acceleration. Okay? So the thing will start to spin faster or slower depending on which way the torque is. And the spinning up or the slowing down of the angular speed, angular velocity, will be in the same direction as the torque. Okay? Just like this, the acceleration is in the same direction as the force, net force. All right, but wait, what the heck is this crazy I? It is the mass. It's the rotational equivalent of mass. Mass provides inertia. This is what's called moment of inertia. All right? It's a really crazy name. Why moment? Moment has to do with the torque. It's not like moment as in it just happened this moment.
So if it's like something spinning around and you're like losing mass and you have to like figure out that mass, is that what they do?
Well, okay. Moment of inertia has to do with its rotational inertia. Okay? So like everybody stand up quick.
Yes.
All right, stand up. Go like this. Stand right here. Put your arms in tight or like this. Here, pray that it'll end. All right, and go like this and rotate back and forth like this. Okay? Feel how much torque it takes to do that? Okay, now put your arms out. Now do the same thing. Feel the difference in torque or the difference in inertia that you have. Notice it's harder to stop yourself from spinning than this. This is really easy to start and stop. This is harder to start and stop. In fact, do this real fast. Now do this real fast. Did you hear your back crack? All right. Now, everybody, you have the exact same mass, right? You had the exact same mass, but your mass was differently distributed radially from the rotation axis. So when will you have greater moment of inertia, greater rotational mass, like this or like this? Like this. Okay. Gymnastics. How many of you watch the Olympics at all? Okay. All right. Gymnasts, actually either Winter Olympics or Summer Olympics, gymnastics and Summer Olympics, and high diving, or, well, diving, in the Olympics in the summer, and in the winter, ice skating has a lot to do with rotational inertia, or your rotational placement of your mass. When you want to spin around faster, what does a gymnast, a diver, or a ice skater do?
Tuck.
They tuck in, either tuck this way if they want to spin this way, or they tuck this way if they want to spin this way, right? Right? Okay, when they want to slow their spin down, what do? They open out, right? They either open out this way or they open out this way, right? Like a high diver, they dive, and when they want to spin fast, they tuck as tight as they can, and then when they enter the water, they magically lift out, and it looks like they stop spinning, but do they really stop spinning?
No.
No, in fact, their rotational momentum is exactly the same. It's just that they've opened up their moment of inertia to make it a big number, and so their rotational speed slows down, which is really crazy. But like if they did that early, like halfway down, they opened up like this, they wouldn't like go, boop. They'd go, then they'd go, all the way down. All right? They can still belly flop.
That's why
That's right. They can still do a face flop. That's right. All right.
That would hurt.
So we're going to talk about this rotational stuff in about a week. All right? We'll get there. So let's erase that for now. Okay, let's talk Newton's third law. Okay, what's the third law? The one that we essentially skipped for most of physics. We talk about it briefly, but then we don't really do much with it. Yeah, it's the action-reaction one. Okay, it's commonly referred to as for every action there's an equal and opposite reaction. That is incorrect. It's for every force there is an equal and opposite in direction pair. Okay? For every force, there's another force, exactly the same size, but in the opposite direction. Now, so it's a force-force pair. For every force 1, 2, there is a negative force 2, 1. Okay? And the confusing part about it is that students tend to think that that means that for every force there's a canceling force. That is not correct. Because these forces act on two separate objects. It's when one object interacts with another object, they apply equal and opposite forces on each other. Okay? So, okay. I run down the hallway and I run into a really big person. Okay? Okay? I run into Dr. Tuttle. Okay, I'm running down the hallway, I run into Dr. Tuttle. Okay. When I run into Dr. Tuttle, who loses? Me. I lose.
Why were you running down the hallway?
SEM loses because those two are
Being chased by angry tag students because I had SEM cartoons. All right. So I run down the hallway, I run into Dr. Tuttle, I lose. Now, the thing is though, is I apply a force on Dr. Tuttle when I hit him. He applies a force on me. Those forces are equal, but in opposite directions. So if I'm running this way, the force from Dr. Tuttle on me pushes me which way?
Back the way you're going.
Okay, so what happens to me? I hit, and I go this way.
And the tag is attacking.
But what do I do to Dr. Tuttle?
Move him.
I apply a force that way, which does what to him? Makes it,
Makes it double.
it does less to him because he has more mass, right? So the deal is this, here's me, here's Dr. Tuttle. All right?
That's so big.
Here's Dr. Tuttle.
It got bigger. I like how y'all have the same height.
All right. So Dr. Tuttle applies a force on me. I apply an equal and opposite force on Dr. Tuttle. They are exactly the same. Okay?
I like your arrows.
Why, thank you. The deal is this. I have this mass. Dr. Tuttle has this mass. So what does that mean? F equals ma for me.
The accelerator.
It means F equals ma
Negative.
for Dr. Tuttle in this direction for him and in this direction for me. Okay? Same exact force, different reactions, different effects because we have different masses and it happens in different directions, opposite directions, right?
Yes.
Okay, yeah.
Does that mean that anybody who headbutts another person is just an idiot?
Yes, you see that in the movies all the time. You see like these people fighting in the movies and the hero headbutts the bad person and the bad person crumples to the ground and the hero goes on to headbutt more people. Okay, the deal is that's not very bright. Because if you headbutt their head, you're going to crack both your skulls. If you're going to headbutt somebody, where would you headbutt them?
No.
No.
In the
Someplace where it's going to hurt them more than it's going to hurt you, right? Okay, so the thing is, it's like, for instance, if you're going to hit somebody, okay, not that I'm encouraging you hit someone, but if you're going to hit
Hit
someone,
him in the stomach.
yeah, where do you hit them? Hit them in the stomach, hit them someplace where it's going to hurt. Do you, if they swing their fist at you and you swing your fist at them and you hit fists, what good is that going to do? You're both going to break your hands, right? Yeah, that's right. Yeah. I'm going to shake your hand instead. All right. So the deal is this, is that whenever a force is applied, an equal and opposite force is applied. They just happen on opposite objects, so you get opposite effects. So here's the deal. All right, so here's your car. Your car, how does your car move forward? The wheels turn, causing friction on the ground. Now, which way is friction on your car?
Any direction that you're driving.
If you're moving this way, then the friction is this way on your tires. That's because your tires are trying to slide backwards, right? Tires are trying to slide backwards, so friction from the ground pushes your tires forward. So wait a minute, so what happens to the ground?
Nothing.
The ground gets an equal but opposite in direction force. So the ground gets, let's say you're a rear wheel drive car. So you only have one tire that's trying to make you go forward, your back tire. So what does it do to the road? The road gets a friction force this way, equal but in opposite direction. Now under normal circumstances, that does nothing to the road, right? But what if you're on gravel? The gravel shoots backwards while you shoot forwards. Now why does the gravel shoot backwards faster than the car goes forward? There's less mass than your car. So wait a minute, when you're on asphalt, why do you shoot forward and the ground not shoot backwards? Because this is the earth, and here's the mass of the earth.
You can't move the earth.
Here's the mass
That
of
would
you.
be really scary.
Technically, yes, you could. If you've got a bunch of cars all around here,
We can run.
I told you that we could run back, but nobody listens to
Run
me.
back where?
If everybody runs in one
so in
direction,
theory,
opposite of the orbit.
in theory, you could get cars all along the equator and have them accelerate east and make the earth stop rotating.
Would that really
That's
work?
right.
No, why won't it work?
It's still not big enough.
It's still not big enough. The mass of the earth is so big. But if you had enough
Horsepower.
friction force, technically, yes. But what that would mean is that the earth would stop, but then all these cars would be ripping around this way, right?
Don't stop.
But then what would happen when the cars stop?
They're gonna fall off.
Start back up again.
The earth starts spinning again.
We would stop time.
What's that?
We can stop time.
No, we can't stop time. I know, that's what Superman did.
Oh, yeah, that was awesome.
But that's not real. You cannot stop time.
So how can you, I don't know, like move something that's more massive?
All right, good question. Common question is how can you move something then? If this,
More so, right?
let's make it simple. Let's say I have a box sitting on the ground.
Your box.
And it's a giant box.
It's a giant box, and here's you
Oh, my.
pushing on it.
You're great. Like,
All right, and here's the earth.
Big box.
Okay, we have these three objects interacting. I want you to draw the free body diagram for each one. Draw the free body diagram for the box, free body diagram for the person, and free body diagram for the earth. Let's draw those three free body diagrams.
You're pushing on
What
the
are the
box.
forces that interact between all of them?
What's going on? The person's pushing the box?
The person is pushing the box.
Okay, well then,
Yeah, it's over.
Okay, let's handle it one by one. What are the forces on the box?
MJ.
Weight down,
MG.
and then pushes it.
What are the other forces on this person?
Push.
Which way is the push force on the person?
The other way, backwards.
Notice that this one is the same as this one. Now, if you don't believe that, try this sometimes after an ice storm. Go outside, try to push your car forward when there's ice on the ground. What happens to you?
You slide back.
You slide backwards because the car pushes back on you. Right? Okay, there's another force on the person.
Force friction.
Which way is the force friction on the person?
To the right.
Forward.
To the right.
Which way is the person's foot trying to slide?
Backward.
Backwards, so friction is forward.
Same thing with the tire.
Force friction 2, force friction 1. Oops, sorry, 1. All right? Now, everybody, just looking at this, if the person is going to move forward, what has to be true?
friction has to be greater than.
Force of friction on the ground has to be greater than the pushing force.
Yes.
If the box is going to move forward, what has to be true?
Push. That's
The
the
pushing force has to be greater than the friction force.
Yes.
Okay? All right, so here's the deal. If I try to move a big box across the floor, then I'm going to have difficulty unless the friction here is less than my friction with the ground, right?
Yes.
I can't do it unless that's true. So generally, what do? We put this box on something that has less friction, like rollers or something, right?
Yeah.
Okay, ice, little hovercraft. Actually, they have those industrial hovercrafts where you just air the thing up and you push it around the plant. It still has mass though. So like if you get it moving, you still have to stop it, right? Okay, so friction 2 has to be greater than friction 1 for you to move this thing. Okay, what are the forces on the earth? Oh.
MG2 down, MG1 down.
Ah, very nice. We have up, down, equal, but opposite in direction. MG2 up and MG1 up. Okay? What else? Oh man, we got normal forces. So we got normal 2, which way?
Down.
Down.
Oh wow, this is gonna be.
This is going to be crazy. What do we have over here? Normal 1 down. That's not it. What else?
Friction.
We got friction. Which way is friction here?
To the right.
We have friction 1 to the right, and over here we've got friction 2 to the left. Ah!
So.
Now everybody, make sure that you understand this. Now, notice that this normal force comes from the earth, so these two must have an equal and opposite pair. That gravity comes from the earth, so these two have an equal and opposite pair. And the friction is between your foot and the earth, so you have an equal and opposite pair. The push force is not with the earth, so that's not reproduced down here. So we have 6 forces on the earth. Okay? Now, this is important for you to understand because we're going to end up with problems like this. We have an object on top of an object being pulled. And it's important to know the forces that are acting in between those two objects because they may not be moving together. One may be sliding over the top of another. You know the magic trick where you have a table set up with food and everything, and then you pull the tablecloth underneath?
You can do that?
where this slides underneath what's on top, we're gonna solve problems like that. Okay? Can I do that? I've done it before, yeah?
Successfully?
Yes.
Really?
How many
Yes.
pieces of?
In fact, it's really not that hard. As long as you know a little physics. Number one is you want your tablecloth to be as slippery as possible.
Like silk.
Silk will work. Great. Also, you don't want a lip, like a hem on the edge of your
Oh, my
tablecloth,
God.
right?
Yeah.
A little bump. You also want your plates and dishes to have a smooth bottom, not like a stoneware, rough sandpaper bottom, but a smooth bottom. You also want food on the plates, and like
Oh, yeah.
water and stuff in the glasses. Why? Not more weight, more mass, right? Because an object in motion, object at rest wants to stay at rest, and the more mass it has, the more inertia it has, right? Makes it easier. Everybody goes, oh, you're gonna spill the food. Ha ha. Makes it easier, right? Makes it a lot easier. All right.
Can we do it?
You have a
Uh,
party and we'll do it.
And
we
then
have a
eat.
party. Put all the pizza boxes on top.
Oh, we should do that. Pizza pizza?
Yeah.
Okay, 6 months now.
Maybe Mr. Ruin, this year we can actually build a hovercraft.
You know, nobody ever brought in plywood. We could have built it.
Oh my gosh.
That's really bad. Okay, everybody, here we go. Let's go through our forces. Here's our different types of forces. In fact, you tell me, what are all the forces we need to know? Force friction, there are two types of friction, right? Static and kinetic. Okay, what else? I think somebody said normal. Gravitational. Electric.
FB.
FB. What else?
Nuclear force.
What?
He's saying weak nuclear.
No, not weak. Not weak and strong nuclear force. We're gonna get there. And not V force from Star Wars. All right, what else? Spring.
And tension.
Tension.
Centrifugal.
You don't.
No, I'm kidding.
I'm gonna throw you out of class. I'll put centripetal down, but it's not a real force. Okay?
Yes. What else?
Actually, we call force a centripetal force, but it's not a force unto itself.
Yeah, it's
It's accumulation of forces that cause you to go in a circle, or cause you to turn. Buoyancy. Okay, things that you've missed would be weight, spring, tension. We have tension, normal force, friction force. Drag. That's a new one. All right, so here we go. Let's start from the easiest. Weight. Okay. F sub g equals mg. It's a special case of gravitational force when little g is approximately constant. Okay, if little g is approximately constant, we use mg. All right? Because it's really this. F sub g equals negative g m1 m2 over r squared. So everybody, would you please write this down? This is the first derivation you'll have to make somewhere in the class, and it's not on your equation sheet. Excuse me. Gravitational force equals gravitational force. Okay? So that equals mg. Now the question is which m is this? Is it m1 or m2?
Well, just whatever we call it.
Mass 2, mass 1. And which one goes away? Mass 1 or mass 2?
Mass 1. Mass 1. Mass 2.
Mass 2 is part of little g.
Which one are we figuring the weight for? U probably, right? Mass 1?
And its own gravity.
Okay, so the deal is this, what's left behind is the mass of the planet, and so we generally will call that capital M, just to remind you it's the big mass, all right? So what does that mean? It means that little g, the acceleration because of gravity, is negative g capital M over r squared. Now the negative means the direction, so what's the direction? Towards the center. It means negative along the radius. The radius is from the center of the earth outward. So negative just means it's going to be down, opposite to the radius. So I'm going to get rid of the negative because I think all of you will understand that that g is downward towards the center of the big massive object. So what is g? Little g is big G, the mass of the planet, and what r?
The radius of the planet.
The radius of the planet. So I'm going to make that capital R.
Isn't it the radius from the center of the planet to the top of the object?
Actually, it's from the center of mass of the planet to
Oh,
the
yeah.
center of mass of you, in this case.
Okay.
But since you are so small compared to the planet, it's generally accepted as just the radius of the planet.
But what if you like fuse Pluto and Neptune?
What is it?
If you are sizable in compared to the planet, then yes, you better take that into account.
Okay.
But if
All right.
we can do that, then
All right, so here's the deal, everybody. When is little g approximately constant? Okay, that's a constant.
Yeah.
That's a constant.
When R is a constant.
When the change in R is small enough you don't have to worry about.
So if we
So-
blow up the earth in half, then
You bet.
we
Well,
what?
if we
When you're
if we
sending a
blew
rocket,
the earth
right?
in half,
Yes,
it
so
would
when does it
still-
make a difference? It makes a difference when you send something out of the atmosphere. Now, on Earth, if you like climb to Everest, the highest place you can get, compare that to say like Death Valley, or like the Dead Sea area where it's way below sea level. Okay, the deal is that's about a 1% difference, maybe, in little g. So we generally don't worry about it on Earth. We call everything, when we figure out gravity on Earth, we just use mg with g being 9.8, little g being 9.8. All right, it's not exactly 9.8 everywhere, but close enough. Okay, close enough for what we're going to do. Now, if you're NASA, you're going to send stuff into space. That's not good enough. You'll use this.
Who's
You'll
the
make
only
it out.
guy using it?
Little g. Yeah, if you try to use this, sending something to the moon, you're in trouble. You're in
What did he
big
make
trouble.
it?
Okay? All right, so there you go. By the way, yeah.
What about when the object is not circular or spherical?
You mean like a planet?
Like a square box or something? You
Okay,
know?
like the Earth is not really round.
Yeah.
It's kind of an elliptoid. It's fatter around the equator because of the spin. And so actually at the equator, your G is not 9.8. It's a little bit less. It's like 9.7
So do
something.
they teach that in school, like?
No, not really. For us, it doesn't. For what we're talking about, it doesn't make a lot of difference. But like if you're doing some sort of experiments, it will make a difference. Like we could measure G here, and it won't be exactly 9.8. It'll be close. All right. Plus, at the equator, the spin of the Earth is trying to sling you off, so you weigh a little less. You'll weigh most at the North and South Pole.
So if you
You
want
wanna
to
lose weight, go to the
You build a real tall platform at the equator. So you climb Kilimanjaro. It's a really high spot on the equator.
And you wear less.
That's right, you weigh less. Same mass, but you weigh less.
Who's gonna-
Okay, all right, we got that. Piece of cake. Okay, let's go to our next ones. Let's go to some easy ones. Normal force is a perpendicular force of contact. Normal force is a contact force that's a perpendicular. So you only have normal force if you're in contact with an object, okay? So like a lot of times we'll have students draw a normal force on an object that's in the air. No. It all has to be touching something. So like right now, I've got two normal forces. One for my feet, one for my hand. They're both perpendicular, so one's up and one's out. Okay? All right, tension is also a contact force. Okay, it's a contact force that acts along an object. Okay, so like if you try to stretch an object, it pulls back. Okay? Both of these forces are lazy forces, meaning that they only do what's necessary. The more you try and stretch an object, the more tension will be. The heavier you are, the harder you push on the floor, or the harder you push on the wall, the bigger normal force is going to be. Okay? So there's no set equation for these. All right? Let's go. Okay, these two right here, we'll talk about those when we get to E and F.
Thank God.
Yay, team. Okay, buoyancy force. That's not covered in this physics C.
Yay! I like buoyancy.
It doesn't hold water in its class.
Oh, why are we happy?
It's rho VG, but it's not. We won't cover it in this class. It's not in mechanics.
Well, I like that.
I know. It's cool.
No wonder it's all good.
Okay, spring force.
Oh, much instigators.
Negative Kx. Now that is what's called a Hookean spring, meaning that it follows Hooke's law. That's Hooke's law. Meaning that the,
Seriously?
yes,
Hookian?
that's correct. I'm not just making that up. Really? If you stretch the spring a meter, it'll exert a certain force. If you stretch it 2 meters, it'll exert twice as much. Okay? That's called a Hookean spring, or a spring that follows Hooke's law. Okay, here's the deal. Not all springs act that way. Like for instance, like elastic, like a rubber band doesn't act that way. If you stretch a rubber band, the rubber band gets its spring constant goes up as you stretch it more, or sometimes they'll model it something like this. There are other types of springs, say like that, or like that, with a different power to act. Okay? So like which one of these would be the hardest to stretch farther and farther?
When do you know which one is which?
Okay, they're going to have to tell you. Unless otherwise specified, we will assume our springs are like this. But occasionally we will run into, in this class, a spring like this, or a spring like this, or something else. Okay?
Will it tell us that it's
Yes.
it's that equation?
Yes, they'll have to, because otherwise we won't know, right?
What springs are most likely to be Hookean? Are they like tightly coiled, dense, or?
You know, just a regular coiled metal spring. There you go.
Good enough.
Good enough. In fact, most of these, if you stretch them just a little bit, they'll behave a lot like this. Actually, the spring that you have like in your ink pen, that little spring, we know that there are limits to this, because we can't stretch that a meter, right?
Yeah.
So if we get past a certain spot, it's going to not come back, right? You stretch it out and you deformed it and it won't go back. So, I mean, there are limits to this. This is still an approximation when we're in this linear zone. By the way, everybody, the negative sign is simply to tell you that the force is backwards in the opposite direction of the way you stretch the spring. So if you stretch the spring to the right, the spring force is to the left. If you compress the spring to the left, the spring force is to the right. There you go.
Wait, but if you if you pull it out like this and kind of they both do the middle.
Say that again?
If you pull it out like this and it do the middle.
If you let them go.
Yeah, if you,
Put it on
They
move.
both do still be like that.
it's like if you take both ends of the spring and pull both ends, then it'll pull back this way and this way. And then if you let go,
You know what I mean, like.
Yeah, if you do let go sometime, they both.
But they'll both be like that when they're still holding it, right?
if I take the spring and pull it like that, then this end of the spring pulls that way and this end of the spring pulls that way.
So they're, okay,
Does that make sense?
yes.
All right. Okay, what are we down to? We're down to the fun nature of friction.
Yay.
Okay, first of all, friction is a contact force. Now we're talking friction of objects sliding past each other. Friction is a contact force that is parallel to the surface. Okay, so we have a perpendicular here, we have a parallel one here. Okay? Now remember everyone that static friction is a lazy force less than or equal to mu force normal. And normal force does not mean mg. It could be mg, but not necessarily. Okay? In fact, since we're in physics C, what's the chances that normal force is going to be mg?
0.
Yeah, not likely most of the time. Okay? They're going to have some weird contraption, some arrangement, so that normal force is not going to be mg. So don't put mg in here unless you're sure it's mg. So,
The way I think about it is like, the more I push down on the ground,
yeah.
the harder it is to like.
That's correct. That's correct. So like, for instance, if like, when we had that picture of that box, and say you're trying to push this thing, but you're unable to get it to move, because your friction is less than the friction on the box. So the friction keeping the box from sliding is greater than your friction pushing it forward. Knowing this, what can you do?
You can lift.
If you can lift the box up some so that it has less normal force between it and the ground, then its friction will go down. And in the process of trying to lift the box, what are you doing to yourself? Pushing yourself into the ground, increasing your normal force, which increases your friction. It's like they do this in football all the time. Linemen in football, when they battle each other, a lot of it is getting low and getting under the other one. Because if you get under the other one and you push up, you get more friction, you release their friction, because the normal force is less on them and greater on you, and so you're able to move them out of the way. Yeah. Yeah, actually, that has to do with your back. Like if you lift a box like this, then you're torquing your back down, and your back is made to withstand a lot of weight vertically, but not a ton this way. The lateral support on your back is not as great as the vertical support. So that's why they tell you to bend your knees so that your back still stays mostly vertical. All right, everybody, I want you to really remember this. Careful, caution, caution. This equation is almost of no use to us. All it tells us is the maximum static friction. It doesn't tell us the real static friction unless we happen to be at the maximum. Okay? So unless you know you're at the maximum static friction, then this is no use to us whatsoever, but to tell us what the maximum can be, but doesn't mean that we're really there. Okay? Please be careful. Now, kinetic is great. Kinetic is an equal sign. We can use that till the cows come home. All right? Now we have one more equation, and that's drag. Now we're going to talk about drag specifically all one day. Force drag equals BV to an n power.
We've never done drag.
We have never talked about drag. Sorry, we've never done drag. We've always conveniently neglected drag.
I like those.
Drag is a frictional force that acts between a solid object in general and a fluid. So moving through a fluid. It's like all other drags, it's like all other frictions, it opposes the relative direction. Okay, so like if you're moving through the air that way, drag will be that way. If you're falling through the air, drag's up. Okay, the deal that makes this one so different is B is a constant. B is like your drag coefficient. It tells you how slippery you are to the air or the fluid. Okay?
So it's the drag constant of the object.
Yes. That's correct. So like for instance, if you fall through the air like this, or if you fall through the air like this,
Ready.
okay, and you're falling down, okay, which one has a greater B?
The one
One
vertical.
Okay, this one will have more drag than this one, right? Okay, so B has to do with the shape and size of the object, its orientation, and also it has to do with the fluid itself. Like for instance, if you're doing this in air, or if you're doing this in water, you're going to get a much bigger B, drag coefficient essentially, this way in water than you will in air, because air is thinner, right? If you do this in mercury, you have a really big drag coefficient. Okay? Mercury is heavy and massive, hard to move out of the way. If you do it in molasses, it's going to be really big. It's sticky, right? High viscosity. Okay, here's the other thing, everybody. Drag force depends on velocity. Instantaneously. So, my question is that, well, you've done this before. You've all driven down the road and you stuck your head out the window?
Yeah.
Right? Your head out the window, or if you have sunroofs, stick your head out.
I've done that.
Right? All right.
Well, not winter, but actually.
20 miles an hour, great. 40 miles an hour,
Wonderful.
not so bad. 60 miles an hour, okay, it's getting difficult. 80 miles an hour, not a good idea. Right? Because the thing is the faster you go, the bigger the drag force is, right? Okay, so all of you are going to do this on the way home, right? Stick your head out of the bus, 80 miles an hour, lips are going to be flapping.
The bus won't go 80 miles an
Yeah,
hour.
the bus won't go 80 miles an hour. Tops out at 20. Okay, N is a power. All right. It depends on the type of fluid you're going through and how fast you're going through. When I was aerospace engineer, this N was 2 for air. Okay, we always had V squared. In liquids, I think it's mostly 1. But it could be some other value. So like for instance, in air, we usually did this. It was 1/2 rho V squared. No, sorry. 1/2 rho C V squared. Okay, this is what I used when I was in aerospace engineering. Okay, so V squared. So N was 2. What's this?
That's B.
That's B. Okay, rho is the density of the air, and C is the drag coefficient. Okay, yeah.
What's B for us?
B for us will be given, or you'll have to calculate it. Okay?
But no, I mean like, what is
B has.
Oh, B for us, it's a constant for whatever the fluid you're going through. It's a combination of a number for the fluid and for the shape of the object.
So they're obviously. So there has to be like.
Yeah, so there's ways of figuring out what that B is, depending on whether if you're in a liquid, B is going to be higher. If you're in a gas, it's going to be lower. If you have a jagged object, B is going to be higher. If you got a smooth shape, B is going to be lower. Okay? But they'll give you B, or at this stage of the game, they'll just give you that constant, or you'll calculate it.
That's your old job, we're on about that.
Okay? What's that?
What are the units?
Got the dragon, that's your old job.
I didn't in my position there, but a friend of mine did. He was an aerodynamicist, and so he used that a lot. Okay, everybody, here's the deal. All right. This equation right here we'll use, and it's going to be a little more challenging to us because force is now a function of velocity. And so it's going to be a little more challenging as far as force. Does everybody see the drag force increases as you pick up speed?
Yes.
That's where we did last time.
Yeah, this requires calculus. So here's the deal, everybody. Eventually we reach what's called terminal velocity. In terminal velocity, your mg down and your drag force up are equal. Okay? And you no longer accelerate, and you've reached a constant falling speed. Okay?
Yes. So do we determine the unit of B based on N?
Yes. Let's do that.
Just like that.
All right. Now, everyone, I'd like for you to write F equals MA for this situation right here.
Okay.
F equals MA. Which way do you want to be positive?
Down.
Down? Sounds good? All right, write F equals MA, please.
How was this? How was this thinking?
All right. What does it look like?
NG minus BV to the N equals NA.
All right, does anybody see the difficulty we're going to have with that solving it? Yes.
Velocity changes.
As velocity changes, your acceleration changes. And so here's what we're going to end up having to do, everybody. Here's our next step.
Oh.
And what do we call this in calculus? Thank you. It's a differential equation. We will separate terms. We'll put all our v's on one side. We'll put our t's on the other side. And we will integrate both sides.
Yay. That's exciting.
All right? So we'll get, this will be the one spot, one of a couple of big spots in mechanics where we will have to use calculus because we can't solve it any other way. Okay? Other than that, there's not a ton of calculus. In fact, this is the most challenging of the calculus problems, I think, in mechanics. Okay? Yeah, it's not too bad. There's a couple of moment of inertia ones that are challenging,
Yeah.
and then there's this one. And that's it. This requires a U substitution to solve it. All right, so we have about 10 minutes? No, we have about 20 minutes, right? Okay, we got about 20 minutes. What we're going to do for the remainder of this time is we're going to do nothing but draw a free body diagram. Okay? Because, here you go, everyone. Listen up. In order to solve any problem, or attack any problem or anything that you're looking at with F equals MA, then we must have a systematic approach. Because our little equation, F equals MA, seems deceptively simple. But the real issue is that it's adding up all the forces. And the deal is that the very first thing we have to do is draw a free body diagram. Okay? And on our free body diagram, we draw all the forces. We draw a simplified picture, draw all the forces. No accelerations, no velocities, no displacements, no other vectors, just forces in the right direction. Once we do that, we ask ourselves, is it accelerating? Because if it's accelerating or not, that determines what's the easiest, usually, sign convention to use, or coordinate system. So we pick our coordinate system next. Okay? And then we set up F equals MA for our coordinate system. Okay? And then we solve. That's how we work these every time. We have to draw a free body diagram because there's almost always going to be some, in physics C, there's almost always going to be some sort of something not straightforward about one of the directions. Okay? You're going to have an angle, you're going to have something weird, an extra force you didn't figure on. And so we want to make sure we decide whether it's accelerating or not and pick our sign convention. Okay? Let me give you an example. Okay, you've got a cart that you're pulling along. Assume there's friction. What are all the forces on it, real quick?
Friction.
Okay, there's mg, there's friction, there's normal, and your pull force. Okay. If it's going to accelerate, which way?
Wait,
To the right.
Yeah,
wait, friction goes that way?
because if you're pulling it that way, it's going to want to move that
Just
way,
thinking
so
about the
friction's that way.
wheels.
Now, this is different than the car.
Why is it different?
It's different than the car because the car, the wheels are trying to turn. In this one, the wheels are not trying to turn themselves. They're just being pulled along. Okay? All right, so which way will it accelerate if it does? To the right. So we pick our sign convention like this, and here's why. Because in the x direction, you'll have F equals ma. But in the y direction, what will you have? F equals 0. Why 0 in that direction?
Because it's not gonna sink below ground.
Because there's no possibility of accelerating up or down, right? Well, unless you really yank the thing hard, right, and lift it off the ground. Okay, now that is opposed to a problem like this. What if we have an object sitting on an incline?
Oh boy.
You got mg, you got normal force, you got friction force, and that's it. Now, which way will this accelerate if it's going to accelerate?
Downward.
Downward. So we set up our coordinate system this way, parallel and perpendicular. Because that means in this direction we're going to have F equals ma, but in this direction we're going to have F equals 0. Okay? Does that make sense? We always want to have one of our directions, if possible, to be acceleration equals 0, so F equals ma turns out to be F equals 0, because it makes life simpler. You can solve this one with this sign convention if you like, but you're going to have an F equals ma in this direction and an F equals ma in this direction, because it's going to accelerate this way, and you have to split your acceleration up into components. You do not want to do that unless you have to, because it's just harder. And we're lazy. I'm sorry, we're efficient, right? Now, there are a couple of exceptions. Well, I wouldn't say exception. It's just if something is turning in a circle, say you have an object going around a turn, okay? Which way will this object be accelerating if it's going around the circle? Towards the center. So we'll set up our coordinate system this way so that we have F equals ma towards the center, centripetal acceleration. And then we might have acceleration that way as well if it's speeding up. But at least we'll have centripetal acceleration in one direction, and we'll have regular tangential acceleration in the other direction. Does that make sense? Makes life simpler for us. All right? Okay. What I'd like you to do real quick is to finish up this free body diagram worksheet. Compare it with your neighbor. Make sure all of yours at your table are exactly the same. Okay? You're going to check each other's work. And I'm going to draw a couple of free body diagrams on the board, for which I'm going to want you to do this as your homework. Draw the free body diagram. And write F equals ma for it.
So the homework is a sheet now.
So the green sheet you're finishing out right now. And making sure everybody at the table is the same.
I'm going to tell everybody this. You and It's a name. Ain't nothing wrong with this.
Right, so this is their dad classes this way. But just one thing you're gonna already right.
Right here's gonna be bigger than this one.
There's two normal.
Yeah, there should be.
like you're only like.
Like you could put
Like,
in
you know,
there
like,
normal, just the opposite. Like, broke it up, just to show you that, basically,
To show them that I know.
that kind of.
Oh, cause think about it, think
Oh,
about it.
that's
This
cool.
one- this line right here is gonna be so
This isn't moving, but it could be
What
normal.
I did.
Everything on the, I put frictions on it. But since it's not moving. It's normal, because he said everything that types is something that. Yeah, I put both of them. I think, yeah.
Yeah.
No, this one, I was talking about friction.
That's all fun.
Frictionless.
Oh, okay, I know.
What are all these drawings?
Oh, wait, I
So what happens if mass one falls over and blocks mass two?
This one, only when they're in contact.
Going along with that diagonal.
Yeah, I put that. Constant terminal velocity. That's because I was sure.
So, now, they have to. Okay.
Which direction is it? At that point, it's moving completely horizontal.
So Jack goes there. Okay.
Because if the velocity
that's enough.
that means
So,
that
some more.
It'd be really attached, or is it falling down in
How's that? I don't know.
Is that like a bug on a wing?
That's right.
Alright. Okay, we have about 6 minutes. So here you go. Here are your 5 homework assignments. Alright. In each case, I want you to pick your coordinate system and build F equals MA for each mass in both directions of your coordinate system. Okay, so like if there's 2 masses here, there will be 4 F equals MA equations.
Each man, oh, okay. I understand.
So mass B is sliding down?
Okay, everybody okay with this? You pick an appropriate coordinate system and then build F equals MA for each mass in your coordinate system. So like this one will get an F equals MA in 2 directions, so like X and Y, and X and Y F equals MA for this one. Okay? So you're going to have to draw free body diagram for each mass.
That's what's keeping it there?
Okay? You can't do this without drawing a free body diagram. So draw a free body diagram for each mass, pick your coordinate system, and then write F equals MA for both coordinates, X and Y, or parallel and perpendicular, whatever it takes, for each one of your masses. So you'll have 4 equations here, you'll have 4 equations here, 4 equations here, 2 equations here, 4 equations here. Okay, now everybody, this first one, you're pushing, or something is pushing along this cart. Mass B is not sliding down because you're moving it fast enough so it won't slide down.
So it's stuck.
It's stuck on the side, but not because it's attached, only because friction. Friction's keeping this from sliding down. This has wheels. Okay, and this one right here, there's friction here. Pull these frictionless. Okay, just accelerating this one down. This one over here, there's friction here between these two. There's friction here between these two. And mass 2 is accelerating this way, so that means mass 1's accelerating that way, right?
Yes.
This is essentially a one-dimensional problem, right?
Yes.
Sort of.
Wait, did you say number 2 is frictionless?
This one has friction.
But M2 is bigger than M1.
M2 has more mass than M1, so it's going to slide this way.
The second one.
It won't matter. You know what? Everybody, let's say this accelerates that way, because there's a possibility it could be stationary.
Yes.
Thank
That's
you.
what I was hoping.
All right, this one right here. You have an object against the wall like this, and you're pushing it up and accelerating it.
Yes.
All right? This one right here,
You're moving the incline.
there's no friction here or here between the ground and this incline or this box on the incline. There's no friction at all. But this mass 1 stays stationary relative to mass 2
Because of my push.
because you're pushing it. Because if you don't push this incline along, this is going to want to slide down because there's no friction. So you're going to push it along at just the right speed so that these two stay relative to each other the same. All right?
What was
I think we can do that.
This one?
Yeah.
There's two masses attached by a pulley. There's friction here, mu2, friction here, mu1, or coefficient of friction, right? Mass 2 accelerates down the incline. That means mass 1 accelerates up. And we had the excellent point that, well, what happens when mass 2 falls off of mass 1? Okay, we're only worried about the spot where mass 1 is on top of mass 2. Okay, I'd work really hard to make sure your free body diagrams are correct. Okay, so check with everybody else to make sure you have the same free body diagram.
Okay.